Hi, welcome to part 2 of our lecture on testing. Before we jump in, let's go through a very important summarization table that gives us an idea about how much variation in the response variable is attributable to unexplained or residual variation and how much is explained by the model. And we do that through what's called an analysis of variance table or an ANOVA table. And this is a basic picture about how ANOVA tables work. There's usually 3 summary lines, a row for regression, a row for residual, this is the unexplained variation row, and then total variation. The size of the estimation and residual spaces will be P prime, the number of regressors. The residual degrees of freedom or size will be the number of data points minus the number of beta parameters in your model. P prime of them are the betas multiplying the regressors, and there's one additional one for the intercept. The total degrees of freedom in a regression problem is n minus 1, and so these degrees of freedoms will add, the regression degrees of freedom and the residual degrees of freedom will add to the n minus 1 total. The sums of squares tell us about the proportional makeup of is the total variation in the response SYY. This is the variation in the response values around the Y-bar response average. You can break that variation into 2 parts, a part due to the residuals, the unexplained part, and the part due to the regression model. And that's the sum of squares column. The mean square column is just the corresponding sum of squares entry divided by the appropriate degrees of freedom. And then the overall f-test can be constructed by taking the mean square for the regression row and dividing it by the mean square for the residuals, and that will give us an overall f statistic and p-value. Let's go through some examples with testing, and let's express a model here with shorthand that says that the y response variable is a function of a factor regressor A, B, and C, interaction between A and B, interaction between A and C, interaction between B and C, and finally a 3-way interaction between A, B, and C. Basically, a 3-way interaction says that the 2-way interaction between A and B changes across the level of C. When you have such a complicated model, there might be all sorts of ways and orders that you might test effects, but we're going to talk about a procedure in a system called the marginality principle. And this principle states that if you're going to study a lower order term, like the main effect for A, you never test that when a model will have higher order relatives, like an A by B interaction or an A squared term. Something that is a higher order, if it has a higher order effect for A, you never will test or analyze the main effect. If you're ever going to do a test for the A main effect, regressors that are not higher order relatives of A, in other words, factor B, factor C, a B by C interaction, those would be included in both the null and alternative hypothesis testing models. Here's some examples. A null hypothesis model has all of the main effects, A, B, and C. It has all of the 2-way interactions. The alternative hypothesis model has all of those effects and the 3-way interaction. This would be a test for the 3-way interaction. If the 3-way interaction A, B, and C is significant, you wouldn't do any other testing because you need the highest order term, the 3-way, and so there wouldn't be any point in analyzing other lower degree terms. If the three-way ABC interaction is not significant, you could test a two-way interaction like A by B with a null hypothesis model that would have all of the main effects and two of the three interactions, but leaving out A by B in the null hypothesis model because we'd be hypothesizing that those effects are zero. And the alternative hypothesis model has all of the main effects and all of the two-way interactions. And so this would be a way to test the A by B interaction. We would test an A by C interaction the same way. We would leave it out of the null hypothesis model and keep it in the alternative. If you were going to test for a main effect like A, you could do it in a system like this. You'd leave it out of the null hypothesis model that would have B and C and B by C. And the alternative would have the B and C factors and then include the main effect of A. This would be a test that would follow the marginality principle. A set of tests that will follow the marginality principle can be collected in an ANOVA table also, and this kind of ANOVA table is called a type 2 ANOVA table. And the way these are always constructed is the last row in the table will have the residual sums of squares and the degrees of freedom and the mean square for the model that has all of the regressors that we're interested in an alternative hypothesis. And this last row, the bottom row of this ANOVA table, is going to be what defines the denominator of all of our F statistics. The rows of the ANOVA table that are above that bottom row are going to be tests, and there's going to be F statistics and sum of squares and mean squares and degrees of freedoms and p-values for a bunch of tests. And let's look at some examples. Here is for a model with the wool strength data, and we're going to be explaining the log of the cycles it takes to break the wool, and we're going to explain log of cycles with a very strange looking model formulation. Basically, this means that we have length, amplitude, and load in all of the two-way interactions. And if you look at the ANOVA table here, you'll see the main effects and all of the two-way interactions. This is a type 2 ANOVA table, and so the bottom row is the residuals for model M1. We have the residual sums of squares, we know the degrees of freedom, and there are no F statistics for this one because this row is the denominator of every F statistic, and so it doesn't have one on its own. All of the other effects are tested in a type 2 manner, marginality principle manner, and the F statistics and the p-values for those tests are given here. Let's go through an example. So if we want to talk about a two-factor interaction test, where does it come from? Well, one of the two-factor interactions are removed from this model, and then they are tested against this M1 alternative hypothesis model. Let's consider the amplitude load interaction right here. Where does this sum of squares and degrees of freedom and F and p-value come from? Well, we remove the amplitude load effect from our model M1. If we do that, the unexplained variation, the residual sums of squares, are going to go up. When we get rid of structure from our model, the residual sums of squares will go up by 0.01 units, more than what was in model M1. There will be fewer parameters in the model. 4 of them will be removed from the null hypothesis in the null hypothesis model. And if you compare the model that doesn't have amplitude and load to model M1 with an F test, you would see a very small F statistic, a very big p-value, and no evidence at all for needing the extra amplitude and load parameters in our model. If we would remove length by amplitude, we would increase the residual sums of squares by 0.4. 4 terms would be removed if we got rid of it. The F statistic compared to this model's residuals would be 4.84, and the p-value would be quite small. Let's demonstrate where that would come from. I'm going to fit a model that does not have length and amplitude. You will notice up here in the M-test model, I have removed the amplitude and length two-way interaction, and I test this reduced null hypothesis model against the full model M1 that has all the two-way interactions in it. And you'll notice the change. Here's the residual sums of squares for the smaller null hypothesis model. Here it is for our full model M1. The change in these residual sums of squares is given right here under the sum of squares change column, 0.401. That is where this 0.40 comes from in the type 2 ANOVA table. You will notice the F statistic is 4.84 and the p-value of 0.028. That illustrates where this F, 4.84, and 0.0281 p-value come from. Again, there is evidence that these particular interaction terms are needed in explaining the response variation. If we would try to interpret main effects, it's going to be more difficult. Let's talk about a term like this load. 2.80 is the sum of squares. Where does that come from? Well, it comes from taking out the load term from a model that has no higher order effects or relatives of load. In other words, satisfying the marginality principle. So that model that we would be using in that case would have length, amplitude, length by amplitude. And we would be comparing that model with a model, this one right here, model M1, and we would get an F statistic of 67.55, very small p-value. That is where it would come from. And so here we go ahead and we do that. We have a null hypothesis model, M-test, that has no load effect. And then we test it against a model that would have the load effect, and then no higher order relatives, length, amplitude, load, and length and amplitude. You'll notice we get a change in the residual sums of squares that is quite big, of 2.8. And that is referring to this residual sum of squares change of 2.8. You'll notice we get an F statistic of 70.9, and that 70.9 F statistic is not equivalent to the one that's given here using these residual sums of squares, because this is not the right one for main effects. Remember, the marginality principle says if you're going to talk about load in a test for load, you can't have any of these higher order interactions with load. So this particular type 2 ANOVA table is not going to be appropriate for testing the main effects. You would have to do that with appropriately structured models. If we wanted to examine another main effect like len or length, when we look at our overall ANOVA table from M1, where does this 12.52 sum of squares come from? Well, it comes from removing length from a model that doesn't have any higher order relatives. In other words, a model that would have amplitude and load and amplitude by load interaction, and then we would remove the length term to get that sum of squares. and the F statistic and the p-value that are given here that you're looking at are using this residuals line for the denominator, which would not be appropriate. To test length, the right test for length would be from using the model that I described previously with length, amplitude, load, and amplitude load terms in it. So the length effect that is showing up here is probably not the one we would actually construct. We would actually construct the one that we've described with the appropriate interaction terms in it. So here is just an illustration of how you would get the main effect test for length. You'd have your null hypothesis model that would not have length in it, and it would not have any higher order relatives, and then the alternative hypothesis has length, and then the amplitude and load terms, and this is where the 12.5 sum of squares comes from, corresponding in this table. Because we have a sort of significant length by amplitude interaction in this set of data, we would probably never be testing this length effect like that because we need the higher order relative. So a main effect test for length would not be supported at all by these data because of the significant interaction between length and amplitude. Well, so far we have been talking about an ANOVA command. I probably haven't stressed this carefully enough, but the ANOVA command that we use to get this type 2 ANOVA table is using the capital uppercase A ANOVA table back on overhead 31, and that produces type 2 tests. If you just take a model and you use the lowercase ANOVA command, you get something that looks similar, but really this is not useful. This command produces a type 1 sum of squares and a type 1 ANOVA table, and this is really not useful because it's only testing the effects sequentially. So a model that has length in it opposed to a model that doesn't have anything, here's the test. Here the line is for adding amplitude to a model that has length. So these are sequential tests, and that's probably not the kind of tests that we'll probably want to ever do. We usually use this lowercase ANOVA command when we compare two models, like we did on the previous overhead 37. So comparing two models, the lowercase ANOVA command is correct and the one to use. When you're looking at just one model, you really shouldn't use the lowercase ANOVA command. You'd use the uppercase A ANOVA command. What we're going to do now is look at a special case when we have category factor and also a continuous regressor. And we're going to think about one category regressor predictor, and we're going to think about one quantitative predictor X, and we are going to consider the different ways that you can have models with continuous and factor variables. And we're going to call those models 1 to 4, and we'll look at their properties and how to test them. The example we're going to use for this investigation is the sleep data, where the base 2 logarithm of the body weight is X, and the D variable is, the danger grouping is the factor variable. And so in this overhead 40, I go through and I make models 1, 2, and 4. Model 1 is the interaction model that explains total sleep as a function of the log body weight, the factor variable D, and the interaction. Remember, this is a shorthand for those three components: D, log 2 body weight, and the interaction d by log 2 body weight. Model M2 is the main effects parallel lines model, and model M4 doesn't have a danger group in it. It only has the quantitative variable log 2 of body weight, and so this would be a single straight line mean function for all danger groups. So again, model M1 will have interaction between danger grouping and the quantitative predictor. That is going to create separate slopes. Model M2 is going to have lines for the different danger groups that have the same slopes, just different intercepts. And model M4 is going to have the same slope and the same intercept for all danger groupings. Here is an effect plot for model M1 that has interaction between danger group and log body weight, and you will see from this display that the different danger groups almost look parallel, even though this is a model that is allowing different slopes for these relationships. They look very parallel. Here is the set of estimates and output summary for the three models. The first column here says M1. This is the model that is the most general, separate lines for every data group, different danger group, different slopes, different intercepts. This is the most complex and most general model we have. Model M2 is the parallel lines model. You will notice that the log 2 body weight only has a single value slope, negative slope, and model M4 has a single slope and a single constant intercept with no other adjustments. You can see the R squared for the single line model is only 0.284, and it's quite a bit larger, up in the 0.5 range for models M1 and M2. And just visually looking at these R squareds, you can see that model 2 and 1 are clearly better than model M4, and we'll learn how to test that with F-tests. Model M2, you'll notice, has separate intercept adjustments for the danger groupings, and those are given here by these coefficients. The blank area in here is for terms and parameters that allow different slopes, and in the main effects parallel lines model, model 2, we don't have separate slopes, so these effects are not defined. In model M1, though, we do have both separate intercepts for the danger groupings and separate slopes for every danger group. Remember that these interaction terms are measuring change in slope from danger group 1, which has this slope of negative 0.403. All right, let's take a look at the capital A ANOVA command for our model M1. We can see from this that the interaction between log 2 of body weight and danger grouping, this would be the appropriate type 2 test effect. It shows only a small change in sum of squares and a very big p-value for this F-test, and there is really no evidence here to suggest that we need separate slopes for the different danger groupings, which would suggest something like model 2 looks like it's just about as good as model 1. We don't need the extra slope structure, separate slope structure for this model. The D line here is, of course, addressing the issue about whether we need separate intercepts by danger group. And this sum of squares is, of course, the right sum of squares for dropping the intercept adjustments from a model that would have a log 2 body weight effect. Remember the marginality principle. It would be testing the effect of these intercepts from a model that would not have these separate slope adjustments. In other words, it would be from a model 2 type of test. So the f-test and the p-value here that are reported for the d effect would not be appropriate. If you wanted to study that, you would do the ANOVA command on the M2 main effects model, and you would get the right sum of squares, of course, the 285, as we suspected, but the f-test would be appropriate to the model M2 f-test. And so what this table says is, if we thought about getting rid of separate intercepts, this factor variable for danger group, it is a very significant change, and we would really gain a lot by having separate intercepts. And so this separate intercepts is a very significant effect, as is the need for the log 2 of body weight in explaining time slept. So the second bullet here shows very clear evidence that both the regressors are needed. This F statistic of 6.37 and the p-value of 0.0003 would be exactly what we would get if we would do an ANOVA command between a small a ANOVA command between M4 and M2. You'd get the same F statistic and the same p-value. The same thing would be true if for the log 2 body weight f-test, if we would remove the log 2 body weight and just test it against a model that would just have intercept adjustments. So it looks very clear that both of these model components are needed, and it looks like a model like M2 is a reasonable one. There's no reason and not a good idea to think a single line is good enough here. So because both of these components, the slope and the separate intercepts and line shifting, appear to be needed, Model 2 looks like a good candidate. If we want to consider a slightly different set to consider, models 1, 3, and 4, remember model 1 is totally separate lines. Model 4, M4, is a single line for all danger groupings. Model 3 says we're going to force the intercept to be the same, but we're going to let each danger group have its own slope. And that's what Model 3 does. So if we take a look at the capital A ANOVA command for model M3, you will see that there is very strong evidence that we need slope adjustments by danger group with this small p-value. And so there is really no evidence here that we would simplify the M3 model. And so at this point, there really isn't any simplification that can be done on M3. When we looked at the other line of investigation, when we looked at models M1, 2, and M4, we came up with the idea that M2 looked like a good choice. So right now we are stuck with two candidate models, model M2 and model M3, and these models are not nested within each other. You will notice that in order for models to be nested, there has to be terms in common except for ones that are left out of only one of the models. And you'll see that these slope adjustments are in model M3, but they're not in M1. And the intercept adjustments are in M2, but they're not in M3. So again, the slope adjustments are in M3 and they're not in M2, and the intercept adjustments are in M2 and they're not in M3, and so these models are not directly comparable with tests. What you would have to do is resort to something like look at R squared, and you can see from looking at R squared, or maybe residual plots or something, you can see that R squared is superior for model M2, and so the parallel lines model looks like it is clearly the better of the two, and that's how we would choose. When we have models with grouping and factor variables, a lot of times what we want to do is estimate group effects or group averages. When there's interactions or other continuous quantitative variables in the models, we would want to compare groupings and effects at certain levels of our other regressors. And these are very complicated and but really important kinds of computations. And so effect plots help us do this, but the workhorse is really the LS means function in R. So let's take a look at an example of how to use it. We have a model that is explaining total sleep according to the danger grouping. This is just a model that has purely factor variable in it, and if I want to compare the average durations of sleep, we do it with the ls means command, the model that I've estimated, MD, and compare groups pairwise according to the danger group. We get a listing of all the group averages, and then we get comparisons. And so this first one would be comparing danger group 1 to danger group 2, and you can see that danger group 1 has about 1.33 hours of sleep more than danger group 2. And so we would compare danger groupings in this contrasts area. If we have a model like we had before with a continuous predictor log 2 of body weight, we could compare danger groupings at a fixed body weight. So back on one of the effect displays, we would be saying, well, let's compare a group at 4,000 kilograms of body weight, or 4,000 grams. Not sure what the units there were, but here's how we would compare those at a particular body weight setting. Here's what the danger group averages estimates would be by plugging in 4,000 into our estimated model. And then here are the comparisons if we wanted to compare 1 to 3 or 1 to 5, 2 to 3. Here are the sleep duration differences depending on which group we wanted to do. So this model is complicated. It was model M1 that had interactions, and if we specify the quantitative predictor, we get very precise and exactly the kinds of comparisons that we would want. We're comparing the danger groups at a particular body size that we're interested in. In this section, we are going to talk again about power of a test. We hope that you have been introduced to the idea of power previously in some other kind of a course. It's just the probability that you would be able to determine that a null hypothesis was indeed false. This is kind of what we hope for when we do statistical inference. We are able to correctly determine that null hypotheses are false when, of course, they are false. So we want this probability of being able to make a good decision to be quite high. We want this power to be as big as possible. And this little section in the book, section 6.4, talks about this probability of f-tests to make correct decisions. And the issue is that there is a non-centrality parameter that basically controls this probability and this ability to make correct decisions. And what determines and what controls the non-centrality parameter? Well, it's how big is the real model effect, how big is the true beta in the data generating system, how much data do we have, n, how much error residual variation around the mean function do we have, sigma, and it also matters about how the regressor data values are distributed. As general rules, power goes up as the data amount, sample size, n, goes up. When we have bigger effects that are happening, the higher the probability we'll be able to observe and determine that those are real. And power also goes up when error variation would decrease. So I want students to think about these issues before you plan a study and you collect data. Make sure you have data amounts that are sufficiently big to find the effects that you hope to find. So let's just take a look at a little example. We'll specify the size of the effect for beta 2 divided by the error variation sigma to be 0.75. And if this is the size of the effect that we want to determine in a hypothesis test, on the next page you'll see that as sample size goes up, the power or the probability that you will correctly reject the null hypothesis that beta 2 parameter is 0. Remember, it's not 0. Beta 2 is really something like this, but if you test against 0, you have a much higher probability of correctly rejecting and getting evidence to doubt that null hypothesis when there is more data rather than less. It's to illustrate the ideas of power. We've been talking a lot about F-tests in this lecture, but there are other kinds of tests that use knowledge about the sampling distribution of the beta hat estimates of how they behave when we repeatedly estimate from data creation systems. So, and these tests are called Wald tests. So what we need to know is that from our regression models, our estimated beta vector has a normal distribution with the true vector beta as the average and a variance matrix V that is sigma squared times x transpose x inverse. We had this in an earlier set of overheads, and this variation matrix can be estimated by just plugging in the residual sums of squares over the degrees of freedom to make sigma hat squared. The most common kind of Wald test is the kind of t-statistic that we see in our model output, where we are testing a beta parameter against 0. There's no reason it has to be 0. In general here, the null hypothesis is that the beta j parameter takes on a null hypothesis value like beta j naught, and the alternative hypothesis is that the real parameter value is not beta j naught. And you can construct a t-statistic using the beta estimate, beta hat j, subtract off the beta j naught, and divide by the appropriate standard error, the square root of the variance matrix entry. And those are t-statistics like we have used in our class. There are other kinds of Wald tests, though. For example, if you wanted to compare a linear combination of coefficients, we can form a function of those coefficients and those parameter values using what's called a contrast. And I've denoted the contrast here with a L. This is a lowercase l, and it's a set of constants, A transpose times the beta vector list. And it'll produce a combination, a linear function of the betas. And we can just plug in beta hats to get an estimate. But the variation requires this kind of formula. The constants that we want to use to construct the combination times the variance matrix times the constants, all square root. Here's a little example. If I wanted to compare beta 3 minus beta 2 from a model, I would have the beta 3 with a 1. The beta 2 gets hit with a minus 1. and that would form a linear combination, and you can use the estimate, the L hat, by plugging in beta hats everywhere, and the null hypothesis value that you were interested in, and then this standard error can get constructed from this formula. And this would be a t-statistic using the degrees of freedom from the model that is being used. You can also construct a test based off of a general linear hypothesis that this complicated function of beta is equal to a vector c, and you can test whether that is a reasonable thing or not using an f-test. The linear hypothesis function in R will do tests about functions like this one. I believe there's some homework that uses that linear hypothesis function. So one of the things we notice is statisticians report and recommend reporting the observed p-value, and make sure you let your reader make their own judgment. Don't impose a judgment of that's significant or something like that. Give the p-value, so if the person reading your work has a differing opinion about what is a small p-value, they can use it themselves. In one of the later sections of this chapter, the textbook talks about an article, Why Most Published Research is False, and the discussion is quite interesting, and it comes from the fact that in real investigations, a lot of the hypothesis tests that should be rejected are sort of small. The real discovery fraction that probably is going on is something like, 1 to 10% of the tests are testing for true effects that are really there. If that's really how frequently real effects are being examined, what will happen is that more than half of the tests that you do, more than half the tests showing small p-values are going to be false discoveries. They're going to be tests that look promising, they have a small p-value, but in fact there really is nothing going on in real effects. There has been studies that have been done about other studies, and most often later on, as research is being confirmed and tested for a second time, no one can ever confirm the findings of earlier studies. And this is a very common phenomenon. One of the other things we'd like you to be aware of is to look at your data carefully and not just do tests. A lot of times by looking at the data and the patterns and the graphs, you might realize that certain tests are not appropriate because of curvature or other kinds of data problems. Another kind of data that you will find occasionally is data that really are not samples from a particular population, but maybe the population itself. And how do you think about randomly drawing from a population when the data is the population itself? It brings up interpretational and conceptual problems about what standard errors and variations in testing might mean when you're looking at the whole thing. So read the text carefully about this, about what you might say, and that you might have to give different kinds of interpretations to your tests. The textbook also mentions this idea of stacking the deck, and here's a case where what they're talking about is that you use the data to identify useful groupings according to what's showing up in your data, and then using these groupings to do tests. And of course, if you found the groupings by looking at your data and finding a pattern that was interesting and using it to make a group, a lot of the effects that you will apparently find will be just an artifact from the grouping that you made. And so it shouldn't be surprising that that grouping would be important in later analyses if you constructed it from looking at the data. Another phenomenon is the idea of file drawer effects. And if you use a typical 5% probability cutoff to report significant results, and you have 100 investigators that are studying the same phenomenon and the same treatment, you should expect that about 5% of the 100 will report and publish significant results, and the other 95% that didn't find anything will just file their study in a drawer. And what will happen is that the studies that appear in academic journals, the 5%, are going to look important to the rest of us because we don't know about the other 95% that got filed away. And this is kind of how to calibrate your reading of literature and understanding about what things mean and don't mean. Also, what happens a lot of times is that some investigations are done under very controlled circumstances or lab settings, and if you move the context out into the real world, you don't find the same effects. The effects you find are partly due to the controlled environment. The biggest problem of all about testing is doing many tests. So for example, if you do 100 tests where each test has a threshold of p-value of 0.05 for being considered evidence to doubt the null hypothesis, you should expect that if you do 100 tests where there's no real effect going on at all, about 5 of them, or 5% of all the tests you do, are going to look suspicious, like there is some real effect and you're finding it. So you should expect about 5 tests out of 100 will show promising evidence, even if there's really nothing going on at all. And the only way to avoid making errors like that is to be a little bit more stringent and strict about when to decide there is evidence to doubt the null hypothesis. And so there are multiple testing procedures and control mechanisms for being a little bit more strict about what signals evidence. And just so you know, the lsmeans command uses adjustments that appropriately adjust for how many comparisons you're making, and being a little bit more strict when you're making more comparisons and less strict when you're making fewer of them. Let me know if you have questions.